We're going to establish some basic convex lens and develop the concept of optical power. From that, we will talk about the rules for how to draw ray diagrams, and then in class you'll have to practice drawing them for various situations. So we've had experience with this before with parabolic mirrors, especially the concave mirror. We're going to do something very similar, but the main focus will be on convex lenses. So you see a diagram at the top here of a convex lens, and we have parallel rays coming in parallel to the optical axis, and we see our reference points that are very similar to what we saw for a concave mirror. So we should have shown this in class already, but if we haven't, basically what happens when you have light coming in parallel, it will bend in such a way, following Snell's law, that all the rays will pass through the focal point. Okay. Now technically the rays refract twice in passing through this lens, but we're just going to have it refract once, bend once, and so like shining a magnifier at the sun, you can focus all the light and you form an image there. Now if you're doing this, I hope you're using a straight edge. Mine's not very practical, but you get the idea here. So let's redefine some of our reference points. There is the focal point, but another important measurement that goes along with focal point is the focal length. Okay, so focal length is given as symbol f, and that's simply the distance from the lens to the focal point. This is something you might actually have to define on a test. That's why I'm taking the time here. So if you're given a lens and you're asked find the focal point of that lens, it's not something you're going to see inscripted on the lens. It would normally come with a packaging, but that aside, what would you do so that you could determine the focal length? That's something you have to be able to do in a lab setting. So what you need to do is you basically got to recreate this process physically, and that's done by placing the lens in front of a light object, a source that has parallel rays. Well, most light sources aren't like that. So if you recall, we can simulate that or approximate that by shining it at a distant object. Okay, an object whose light is essentially coming from infinity, and the classic example is the sun. In our classroom, that would be basically focusing something from, let's say, beyond the windows on the far side of the room. All right, if you got trees or the sky, clouds, and you focus at that, they're close enough that the rays, or they're far enough away that the rays are coming in so that they're more or less parallel. Okay, like a parabolic mirror, you have a center of curvature, and that is also equal to twice the focal length. And that is denoted with, again, depends on whether you're an IB or AP, that's with a 2F or a C for center of curvature. Okay, I'm going to stick with 2F for right now. Doesn't make as much sense to talk about center of curvature. Now a new term here that we have to define, this is more for the IB than anything, is the optical power, which I'm just going to call the power of the lens. Okay, and we can put a little optical in front of it. Okay, and that's the extent to which a lens can refract the rays. Alright, it's just an indirect way of looking at the focal length. The higher the value of the optical power, the greater the refraction, and the smaller the focal length. So there's an inverse relationship there. So the equation is fairly straightforward. The optical power of the lens, P, is nothing more than 1 over the focal length. The units are an interesting unit called the diopter. Alright, some spelling is RE. And by definition, a diopter, DT, is 1 over the focal length. Excuse me, 1 over meters. If the focal length is in meters, then we can say that the power is a certain number of diopters. So it's very, very important that it is in meters. So for example, very often we find focal lengths in centimeters. So if we're asked for optical power, the mistake would be to do 1 over 20. Okay, that is not correct. Instead, we would have to say the power is 1 over 0.2 meters, which is 5 diopters. Okay, going back to this, you could say it's 0.5 per centimeter. That's technically correct, but if we want it in diopters, you have to convert your focal length to meters. Okay, and the optical power depends on two physical factors of the lens, and as does the focal length. That is the curvature of the lens. So if you want a large optical power, so you can focusing more tightly, you make it more curvature. Okay, and also a very important aspect is the index refraction of the lens, which is really what the lens is made up of. Okay, glass, plastic, water lens, air lenses, we'll see, can bend light more or less depending. And the greater the value of either of the above factors, the greater the optical power and the shorter the focal length. Okay, so let's turn our attention on how to draw ray diagrams so that we can form images with these. Okay, so these are just very similar to what we saw for mirrors. Okay, so just review, determine where an image forms and its properties. We need to find at least two rays of light from any part of the object in question, and where they either focus, okay, or converge, or seem to have originated. Okay, and again, we usually represent the object with an arrow. So we've done that before, nothing new here. So let's say we have a convex lens. We'll say we have a focal length. I'm not sure what's on your note sheet. I'm going to put 2 clicks here. I'm going to put the center of curvature there, and we'll do the same thing on either side. So here is F, here is F in a negative sense, 2F, and 2F. And understand, your eye is right to the right of this, looking through the lens to the object, and we've got to understand where does the image of that object appear. Okay, it's very easy to forget this, the physical context. If my eye is here, I do not see this object directly where it is, because when light passes through the lens, it is refracting, and the light is going to either converge or seem to have originated somewhere else, and that's where we want to find where is that image and what are its properties. Okay, so any ray that passes through the principal, parallel to the principal axis, refracts through the focal point. So I'll just put F here. Okay, I'm not going to be able to draw this very well. You can use a straight edge, but if I come in parallel, that's shaky. Okay, we are going to pass right through F, and that ray, of course, is going to intersect your eye. So the image is somewhere on here, on the other side of the lens, or maybe it seems to come from somewhere back behind here. To know where that is, we need another ray, and like a mirror, any ray that passes through the focal point is going to refract parallel. Oops, parallel. So I'll try to make an attempt at that. So passing through F, and then when I get to the center of the lens, I'm going to refract it parallel. That's a so-so job. Okay, so you can see that it seems to be intersecting right there, so let me just get rid of that. And then the third one is actually the easiest one to draw. Any ray that passed through the center of the lens, and this being the center right there, continues straight through. That is akin to a light ray hitting a surface at a 0-degree angle. So if I try to draw this straight through, fudge it a little, and you can see all three of those refracted rays converge at that point. So that's the image of the arrowhead. The tip of the arrow is going to be on the optical axis. So I put my image right there, and we can then talk about its size, its orientation, etc., etc. Okay, so what we're going to do tomorrow is we're going to look at the properties of the images formed by placing the object at various places with behind a convex lens. So like a mirror, we want to look at the following properties, and that is the position of the image relative to the lens, the image size, the orientation, upright or inverted, ooh, that's rough, and of course the type of image, real or virtual. So we'll see many things in common with what we've learned before. Alright, that ends this lesson on how to draw ray diagrams for a convex lens. We'll eventually hit a concave lens as well.